Good morning, everyone who is connected. This is Paco Douglas from the Barcelona Supercomputing Center in Barcelona, obviously. We are ready to start the first Climate Europe webinar, and I would like to welcome Andrea and Geert Jan, and I also thank them for being so kind to contribute to this webinar. It's very nice that you responded so positively with such a short time for announcing it. Also, I would like to welcome the listeners, those who are participating, and I guess that we'll have more people joining in a bit later as the webinar is starting. I would just like to say a few words about Climate Europe and this webinar series. Climate Europe is a coordinating and support action funded by the European Union under the Horizon 2020 program. It's a project coordinated by the Met Office, by Chris Hewitt, and it's basically a network of scientists and researchers who are interested in finding ways to increase the communication between the communities working on climate observations, climate modeling, and climate services, trying to identify which are the gaps and the challenges, and try to document this thing in a series of reports that will be published during the lifetime of the project. So this webinar is the first one of a series that will contribute to the writing of those reports. I invite you to also have a look at the Climate Europe website, and also to ask us any questions that you might have about the project itself. And there are also other media that are being used by Climate Europe. In particular, there is a portal that is used to upload information, and you might also be interested in participating there. So if that's the case, please contact us. The webinar will consist in two talks, one by Andrea Taylor from the University of Leeds, and the second one by Geert Jan van Oldenborgh from KNMI, the Dutch Met Service. Each talk will be 15 minutes long, and will be followed by 5 minutes of questions. And after the talks, we'll have a brief discussion about well, basically what has been said during the presentations, and if people find it interesting, issues that have to do with a couple of questions that have been formulated in the invitation message. I read them again. The two questions are: which challenges for climate modeling and observations are raised by climate services? And the second question is how to manage the situation with the Horizon 2020 work program, where climate services show a tendency to be better funded than climate observations, modeling, and infrastructure. So I hope that you'll be glad to participate during that discussion.
Is everybody able to see the PowerPoint?
Yeah, yeah. It looks fine.
That's excellent, thank you. So, I'm indeed Andrea Taylor from the University of Leeds in the UK. I'm an academic fellow holding joint posts at the Business School Centre for Decision Research and at the University Sustainability Research Institute. However, my background is in experimental psychology with a focus on risk judgment and decision making. And the research that I do focuses on taking knowledge from the behavioural sciences, from psychology, and applying it to some of the communication challenges that exist in the context of climate change, climate risk communication, and high impact weather forecasting. And one area that I'm particularly interested in, and have been for a few years, is the question of how information about uncertainty in climate predictions, projections, weather forecasts can be effectively communicated to different audiences. And so this is going to be the full focus of today's talk. So we know, of course, that uncertainty in climate information arises from multiple sources. From the fact that no model can be perfectly formulated, perfectly initialized, that when it comes to longer-term climate change projections, that these are very much contingent on future human activities. So to encapsulate this, models are formulated probabilistically. Model performance is reflected in measures of reliability and skill, how well prediction systems relative to observation, relative to another prediction system. And multi-decadal projections are scenario-based to try and encapsulate some of the different paths that we might go down depending on what people do in the future. And it's important that these uncertainties are adequately communicated to those who may use this information for decision making or may use it to create data products for other people to use in decision making. Because if it's not communicated, then it may lead to a false sense of certainty. It may lead to a proliferation of errors in future stages of data processing if it isn't adequately accounted for. It can result in maladaptive decision making if decision makers believe that they're receiving something that's quite deterministic and then make plans and decisions based on that. Then it can lead to them not considering alternative possibilities. And ultimately, if uncertainty isn't adequately communicated and results in misses or false alarms, then this can reduce trust in those providing the information, in climate service providers. However, communicating uncertainty isn't necessarily going to be straightforward because the users of this information are extremely diverse in terms of both their needs and their expertise in using both climate information specifically, but complex statistical information more generally. So just to give an example of what this looks like, I've just taken a figure from a recent paper that was accepted by the meeting paper accepted by Bulletin of the American Met Society. This was based on a workshop that was conducted earlier this year at Garrix, where lots of people. Sorry, I've just been told that there's been a bit of a problem with the sound, so I'm going to sit closer to the laptop. So that between, when it comes to the provision of climate information, there's not just one provider and user, there are multiple providers and users. And that information goes through multiple stages from provider to user before it gets to the end user. And at each of these stages, there's additional information about uncertainty being added. And as you can see from the diagram, detail in this information increases as you go across the chain until you get to the end user. And when you get to the end user, you find that in terms of expertise in dealing with this complex information, that this is probably where you're going to get the most variability in knowledge, in expertise and experience. So in terms of some of the challenges that are faced, ones that have been identified and are quite well known within the climate service community, others that have been quite widely reported within the broader behavioural sciences, we have the fact that uncertainty aversion and preference for deterministic information can lead decision makers to reject information about uncertainty or to not pay attention to it. And one challenge resulting from this we've identified in our own work is that if users are seeking out deterministic forms of information, then this can potentially obscure the uncertainty inherent in that information. You can face the challenge that the same information can be interpreted in different ways. So within the literature on understanding of weather forecasting, we find that when you're talking about something like a probability of precipitation, that this can be interpreted in very different ways depending on the receiver. So does a 40% chance of rain mean it's going to rain over 40% of a particular region, that it's going to rain for 40% of a particular day, or that there's a 40% chance that it will rain on, that on days like tomorrow it's going to rain? Then, I mean, looking at the challenge of communicating climate change projections, especially to the public, one of the challenges that uncertainty is often misrepresented in the media and in other sources. So, for instance, that information about uncertainty, about projections regarding particular impacts, is reported on almost as if, or as if, it's uncertainty about the existence of man-made climate change. That people differ quite a lot in their ability to use complex statistical information, and this can have a very strong effect on how they interpret different formats, how much information that they can use. Time pressure can limit ability to attend to complex information, or it can focus attention on very salient points of a particular document or visualization. And so if the most salient characteristics aren't actually those which are the most important, then it can lead to people focusing on the wrong bits of information. And indeed, we find that even amongst experts in similar fields, terminologies differ quite a lot when it comes to talking about uncertainty. So just to give a slightly amusing example of this, I asked a group of my colleagues at the University of Leeds Centre for Decision Research what the word reliability meant to them. So this is a word that's commonly used in the context of climate information, and it's also used very commonly in many other different fields. However, as you can see from looking at the little speech bubbles here, we all seem to define it in quite different ways. So even when you're talking to people who are statistically experienced, very quantitatively able experts in a particular field, you may find yourselves talking at cross purposes because you're using the same terminology to refer to quite different things. The point here isn't that we should try and standardize the terminologies that we use across disciplines, because this would simply be impossible, but that we need to keep in mind that we do use words differently, and when we're communicating with experts in different fields, different stakeholders, we need to establish that we're all on the same page in terms of what we're talking about. So something that is very important, and this is something that within the behavioural sciences we focus on a lot, is establishing processes for validating communication, for making sure that what we're trying to communicate is actually what's being understood by the people that we're communicating to. And the methods needed to do this vary quite a lot depending on the nature of the user group and the size of the user group. So within the context of climate services, you may find that the size and the makeup of a particular group of users is going to vary considerably. So if you just have if you're just having one user or a very small group of users, this may take the form of an iterative process of one-on-one development. A slightly larger sample, perhaps still in the same sector, you might want to use interviews or surveys. If you're trying to communicate with a very large group, such as the general public, then you may want to utilize large experimental studies to really test whether people understand the information that's being provided, whether this is usable to them. And through doing this, one can identify where potential misunderstandings will occur in terms of terminology, in terms of the design features of visualizations, tables, documents, and address them. And to illustrate the importance of this and how this can be done, I'm just going to draw on a couple of examples from Work Package 33 of the Euphorious project, which I recently co-led. So the objective of this work was to test the effectiveness of different approaches to communicating the confidence and uncertainty associated with seasonal to decadal predictions. So my colleagues and I, we developed a set of strategies which we then subsequently tested with different groups of decision makers in climate sensitive sectors, as well as users within meteorological and hydrological organizations. Just got here some of the collaborators on this project. We also need to give credit to both Barcelona Supercomputing and the University of Cantabria for their help with this. So just to give a couple of examples of how we assessed, in this case, understanding, we presented the visualization that you can see here to a group of users or potential users, decision makers in relevant sectors, who reported having quite high statistical expertise. So in the visualization you see here, most likely, this is surface temperature prediction, most likely tercile is represented using color. The probability of the most likely tercile is represented using the size of the bubble. And the skill of the forecast for that particular area, for that particular tercile, is given using the shading. So as I say, we presented this to a group of users, potential users, and asked questions about how well it was understood. And something that we found was that more experienced users were quite good at understanding and interpreting this when level of skill was high. However, far fewer responded correctly when there was no skill in. So you can see from this, and we hadn't anticipated this, that we hadn't sufficiently explained what blank space on the visualization is. Similarly, we presented this simple bar graph to our respondents, and we found that those with less experience of using statistical information, they really struggled to interpret what this graph meant. And we found, on looking closely at where the errors were being made, that these people were actually mistaking the information that we've given about skill, as you can see on the diagram here, with information about probability. Likewise, others were interpreting the climatology line on the graph as information about likelihood. And so had we not inspected the errors that people were making here, we wouldn't have been able to identify that these misunderstandings were taking place. So just to highlight some other key findings of the work that I've been involved in this area, as well as work that's been done by others, both within relating to climate information specifically and to behavioural decision making generally. We found in a few recent studies that preference doesn't always denote better understanding. That's to say that while user preference is very important because users aren't going to want to use information that they don't particularly like or that they don't feel has been structured very well, that we shouldn't always interpret this as indicating that this is going to be well understood. We need to establish both things. We found that identifying or utilizing evaluative categories, that's to say, by labeling, by providing verbal categories such as low, medium, and high to information such as probability, information such as skill, which is often presented numerically. And those who are not very familiar with these concepts already can be difficult to understand. that by providing these verbal categories to help guide people, that this can aid understanding. I mean, from my own perspective, I know that when I was first shown a skill score, I was tried to interpret it the same way you might interpret a Pearson's R correlation. So, but by giving information about such things as no skill, low skill, medium skill, high skill, that although these are determined subjectively, that they can help those with less experience to understand this information. We know that the way that information is framed can affect responses to uncertainty in climate information. So just to give an illustration, there was a study recently conducted by Ballard and Lewandowski at the University of Bristol, and they presented a climate projection to members of the public. This projection was either presented as uncertainty about a particular climate change impact, the anticipated probability of a particular climate change impact occurring at a particular point in time, or they flipped the visualization round and showed it as probability of as the uncertainty as being about when the impact would occur rather than if it would occur at a particular time. And this was found to have a very strong impact on public interpretations of this information and indeed their response to climate change. Another thing that we found is because users do differ so much in terms of their expertise and in terms of the time that they have to spend looking at and digesting information, that adopting what's called a progressive disclosure of information strategy can be one solution to addressing these varying needs and expertise. So that you provide varying layers of information that can be easily accessed. A simple headline that contains a very short summary of the most important aspects of the information being provided, but with progressively more technical and complex information being made easily available for those who need to use it. So in terms of some of the recommendations that we and others have made regarding communicating uncertainty in climate information, and indeed communicating climate information more broadly, we can make the following recommendations. That in developing communications, consider user expertise, the time pressure that users may be under when using the information, the potential for the way that information is framed affecting user response or recipient response, and be aware that uncertainty avoidance, ambiguity avoidance can exist, and that care should be taken not to present information in a way that could be falsely interpreted as deterministic. That when it comes to communication, the optimal solution is to develop highly tailored communications through a process of iterative one-on-one development with users. And I've got here an example, again from the Euporia's project, of a communication tool for the wind energy sector that was produced using this very tailored, very iterative one-on-one approach, Project Ago. However, we know that this isn't always possible because one may not be addressing a very small group of users, one may be addressing a quite large and diverse group. So in this case, as mentioned on the previous stream, then consider using a progressive disclosure of information strategy, providing information in a layered way to really account for and address these different user needs. To identify where misunderstandings of terminology and design features may occur, and to, of course, by doing this, validate the effectiveness of communication strategies in the same, a similar way to one would always validate the effectiveness or validate a forecasting system itself. So thank you very much for listening. I'd just like to say here that we have the Centre for Decision Research and the Climate Change Adaptation Group at Leeds, both of which are very interested in communications in the climate services, climate information area. And thank you very much for listening, and I'm happy to take any questions.
Thanks a lot, Andrea. That was very interesting. We have time for one or two quick questions. Any takers from the floor? Okay, while people decide if they want to ask anything, I have one question for you. Mm-hmm. Well, actually, I have many, but I have to choose one. I wonder if you could say something about the differences in the approaches that you think should be used to communicate uncertainty in projections and in climate predictions. So uncertainties in the next in information for the next few months or even few years, when the information that is provided for mid of the century or the end of the century.
Yes, yeah. I mean, I think this is an interesting question because predictions and projections, the information, the sources of uncertainty are different. Projections are, of course, scenario-based. So when it comes to predictions, the user is in a position where they will be getting, especially if we're talking about, say, a seasonal timescale, where they will be getting feedback experience as to how the forecast has matched their experience of what actually happened. Whereas when you're talking about these multi-decadal projections, often the users, they aren't going to be working at the same place or may not be here when events are realized at this time scale. So I think, yes, when it comes to predictions, that the repeated feedback can help with understanding. And I know that this is something that my colleague, Marta Bruno Suarez, mentioned was happening in one of the Euporius prototypes, where they were working with farmers, developing a land management tool, and they were finding that the feedback that the farmers were getting was helpful in terms of both refining the communication tools and in terms of the farmers' understanding. Now, projections, on the other hand, I personally have a little less experience working in this area. However, my colleague, Susie Lorenz, does have a paper on this in Philosophical Transactions, that's looked at the challenge of tailoring visual communications, climate projections. And I know that she found, as I did, that there wasn't much of a link between users' understanding and users' user preferences. So that was one commonality. But I think that climate projections is definitely an area where there's room for a lot more work on communication in the future.
Okay, thank you. Any other questions?
Yes, one question from me, from Jeanette. In the last slide, you said validate communication. Well, that's important. But how would you do that if you're focusing on a large group? Well, of course, you can check with a small group whether what you want to communicate is really what people understand from it. Mm-hmm. But do you have more ideas on how to validate your communication?
So, yes, I think that's a very good question because it's, we do know that the methodologies that you need to test communications differ depending on when you're working with one person, a small group, or a very large group. So something that my colleagues and I do, because we do a lot of work with members of the general public, where you're talking about absolutely huge numbers of people, is that we will conduct large online surveys or large online experiments where we'll present members of the public with different visualizations or different pieces of information, and we'll ask a series of multiple choice questions to gauge their understanding. And when we look at the data resulting from that, it helps us to see where people are making errors, where their understanding seems to be working, when the understanding is particularly good. Now, my colleague and mentor, Wendy De Bruyne, definitely expert in the field of communication, recommends when you're dealing with large users that you might want to conduct interviews with, say, a small number of users, say about 5 to 10. Look at where their things that they seem to be understanding or not understanding, how useful they find the information, and then conduct a larger survey or experimental-based study, test it drawing on the findings of the initial interviews. And I would definitely recommend a paper which I've added to the reading list at the end of the presentation slideshow, which I hope will be shared.
Okay, thanks a lot. Thanks, Andrea. We have to move on and change to Geert Jan's presentation. So, Martha. So, hello, Geert Jan.
Hi. Can I turn on the video? And I'll try to share the.
Okay, Geert Jan. So go ahead and as you saw, the list of attendance is changing. It goes up and down. People join in and then leave, and so don't be surprised if there are more people joining in while you talk. Here in Barcelona, we are now 3, so Ileana has arrived a few minutes ago. So
hi, Geert Jan.
You might have more questions.
Okay. And,
good.
And Jeanette is sitting in a room 50 meters away from here. Yeah, so please, I don't know whether it works over WebEx, but I prefer to have questions during the presentation because you don't get much feedback when you're presenting this way, and I appreciate it if people have questions to ask them immediately.
Yeah, that's
your microphone and interrupt me.
Yeah, that's perfect. We are just a few people, so there shouldn't be any problem to do this.
So the last 2.5 years or so, I've been busy with event attribution, and I find this a fascinating subject because it combines so much in climate science in a very concrete way. It looks a bit like seasonal forecasting, but there's climate trends in it, there's communication in it. I will not focus much on the communication aspect, although a lot of people in my project are focusing on that. So what is event attribution? I assume that you don't know, so please, if I can skip this, tell me. But whenever there is a... Oops, why doesn't it go to the next slide? Oops. Whenever there is an extreme event, everybody always asks questions about it. So here there's some extreme event, the heat wave in Moscow, the floods in Boulder, a tropical cyclone Haiyan, the flooding of the Elbe in Germany. And whenever this happens, everyone asks, well, everyone, a lot of people ask the Met offices, the media, how aware was it and was it due to climate change? And until fairly recently, the only thing we said, well, this fits into the picture of climate change and generalities like that. But using methods from the detection attribution from IPCC, those are the people that gave us these beautiful statements like it is extremely likely that human influence has been the dominant cause of the observed warming since the mid-20th century. And using offshoots of those techniques, we can actually say a lot more now about extreme events. This used to be the kind of academic timescale of years. There has been the 5th issue of a BAM special report tried to accelerate that. So now in a few weeks' time, the report in 2015 comes out. So that's still 1 to 2 years. And I thought it would be possible to accelerate that and aim for a few days because the big users want that information really quickly because one of the big users is the media and the people reach through the media. So the two questions, how rare was the event? And we usually express that in a return time, like this was a 1 in 100 year event. I know that there's lots of complications in communicating this, but a large target audience is the engineering community, and in that community this is the normal way to express this. It doesn't mean that it occurs every 100 years, but that every year there's a 1% chance. And our PR department has a field day trying to explain that when a little village in the east of the country was hit by a 1 in 100 year rainstorm, that was fine. And then 3 weeks later, it was hit again by a 1 in 100 year rainstorm. And then they had some explaining to do. You have to be very careful about this because for small scale events like these rainstorms, there are actually two completely different definitions, similar to what Andrea mentioned in the 40% chance of rain. There is the definition, how often does it occur at a given location, so right where you live, or how often does it occur anywhere in a country or another region. And these can be completely different for small-scale events like rainstorms. You expect several 1 in 1,000 year events every year in the United States, simply because a rainstorm is so small and the United States are so large. And that's something that you really have to keep in mind when communicating this. And of course, these probabilities can change with times. The second question is, was it due to climate change? And that's an easy one. The answer is no. It was always due to climate change, plus a lot of other things, mainly the weather. So that's easy. But then you have to explain to the people asking this question that they asked the wrong question and that they should ask the question, has the probability changed due to climate change? And that is the formalism that was developed over the last 10 years or so, following an article by Miles Allen in Nature about the flooding of his home in the Thames Valley in Oxford, or almost flooding. I think it just didn't make it to his home. So you compute the probability in the present climate, and you call that P now. You compute the probability in the past climate, or in a counterfactual climate without anthropogenic influences, which only exist in your model, of course. And that's the alternative probability P alt. Originally, the idea was to compute the fraction of attributable risk, which is defined as 1 minus P alt over P now. If it's 1, it's impossible without climate change. If it's 0, climate change didn't make any difference. However, this is taken from medical statistics. However, we find that this is really difficult to communicate, and most people don't get it. And we changed basically to what's called the risk ratio in the same medical literature, and that's just a ratio of probabilities. So you make a statement, this is now 4 times more likely than it used to be, or less likely, or whatever. And of course, uncertainties play a big role here. They're pretty big, as usual, and so you have to do some kind of significance testing, whether it's unequal to 1, i.e. no change at some significance level. So yeah, you get some probability that some probabilities differ, and it took me a while to get used to these things. So I guess, again, this is something that's hard to communicate. So the procedure, we've been doing this on a rapid time scale with a collaboration called World Weather Attribution, which is led by Climate Central in the United States. It involves Oxford, Melbourne, KNMI on the science side, and the Climate Central and the Red Cross Climate Center on the communication side. And after trying it for a few times, we settled on this procedure in 6 easy steps. First, you try to figure out what happened and make an event definition. Then you have to decide whether to do something or not, so you have to have selection criteria. Then you analyze the observations for a return time and a trend. You evaluate your models. You analyze your models for a trend or a difference between the current climate and the counterfactual climate, and you do your attribution. And then in the end, you have to synthesize everything into an attribution statement. And the funny thing is, of course, when we wrote all our project proposals 4 years ago, we only looked at step 5, and we actually forgot the whole context of the other steps. And we found out about these by actually trying it on a couple of events. And one of them I will show here as an example. It's the flooding in France at the end of May 2016. Well, the flooding actually was the first days of June, but the rain fell the last days of May. There was extreme rainfall in the Seine and Loire basins, and we don't have coupling to hydrological models yet, so we cannot attribute to flooding itself. So we had to find something that we could do, and we settled in 3-day precipitation. We thought it was important enough to do the analysis. We always try to involve local experts. So we had a hydrologist from Paris and a climatologist from LSCE. We knew we had all the model output available, and we had time to do it. The last one is non-trivial, we found out, because it's now, as a research activity, we're dependent on researchers being available. And for instance, the heat wave in the United States last summer wasn't exactly the 1 week that all the team was on holiday, so we couldn't do anything about it. If you want to do this as a climate service, you would need actual and compatible historical observations. You can find a good selection now in the Climate Explorer. But of course, a lot of people are working on this in the climate service community. You need expertise on local weather and climate, which factors were important, which ones need to be modeled accurately, which ones are not important. You need access to GCM and RCM data that physically could be expected to describe the phenomena. It makes very little sense to look at thunderstorms of order 10 kilometers in a 200 kilometer GCM. Or if there's hurricanes in the area, you should have a hurricane resulting model, all kinds of, well, for us, trivial observations, which are non-trivial for other people. And you need a set of criteria when to do an attribution study and when to say, well, this is just normal weather, nobody will be interested in the results. And there's a lot of pressure to have an objective set of criteria there, so you don't only look at the ones that have positive influences. And in practice, we find that very difficult to develop. So the next step is to look at the observations. And the first thing is you try to find the return time. For the SANA, we could only say it was bigger than 100 years based on 65 years of observations, daily observations. Of course, there are some countries like France, it's very hard to get at the observations, and so you have to rely on third-party data sets like EOPS and ECA&D, and they only go back to 1950. There is a positive trend to the observations. You can see that on the bottom graph. Unfortunately, it is not significant, so we cannot draw any hard conclusions from that. And we have to describe, one thing that comes out of that is that you get an idea what the PDF looks like. That's the top graph. You have the return period as a function. So the return value is a function of the return period, and a reasonable demand on the model is that it reproduces this PDF. And we do that by fitting it to an extreme value distribution and looking at the fit parameters, doing the same with the models, and then see whether they fit. So if you would do this in the climate service, and of course we want to push this to services as soon as possible, you would have to evaluate the quality of the observations. And that's really a problem in Africa and South Asia. We found that time series was 40% missing data, and some years where the precipitation suddenly becomes a factor of 10 lower because of the misplaced decimal point, and or spikes of 700 millimeter a day, which are mistyped commas because there should be 70 millimeters and things like that. It's actually quite a non-trivial exercise. You have to fit it to some extreme value function, and there are standard R routines for that. You can do it on the Climate Explorer if you feel like it. You have to assess whether the fit is good enough, and finally note the results and compare it with return times from other sources. Of course, hydrologists, in the case of extreme precipitation, have all these tables and do a quick cross-check whether you get the same as them. Then you go to the models. It's imperative to look at quite a few models because any single model will have biases in the trends, and you have to sample the model spread, which is a measure of the model uncertainty. And if you only use a single model, it can be an outlier. Like the Met Office models always show drying trends everywhere in the world, basically. Well, maybe not completely, but to a reason. And you need also models that are on the other side of the spectrum to show whether this is typical for climate projections or just an outlier. Next step is to evaluate whether the PDF simulated by the model is similar to the observations and whether the physical sources of the extreme are the same in the model as in the observations. And for instance, for the SANA study, we looked at this in our own EC Earth model, for which we had done a couple of runs for this, to develop the KNMI scenarios. And we found that the model just couldn't reproduce these summer events, relatively small scale summer events. It's a 150 kilometer model, and the event wasn't all that much bigger, so we had to throw the model out. And then you compute the trends in the historical runs, or you compare with the counterfactual runs, and you make an estimate of the risk ratio. So again, if you would see that in a climate service context, you need quick enough access to model data archives. I try to collect them right now on the data server here at KNMI, but within the next year or so, we plan to go to a distributed computing environment where you use the subsetting facilities at other data archives. The IRESMIP Primavera project is working on that. Lots of people working on that for CMIP6 because the data sets are getting just too large to transfer from one point to another. So we'll have to tie into that. You have to fit to the extreme value distribution, see whether it's a good fit. I mean, there are many places in the world where you have double populations, you have hurricanes that have a completely different behavior from everything else, and you have to see whether your extreme value distribution actually makes sense. You have to consider whether not only the statistical agreement, but also physical agreement. I mean, do you have hurricanes in the hurricane area? Do you have other events? Are the sources of the moisture the same in the models as in the observations? I mean, just have a critical look at it. All models have biases. You have to apply bias corrections, and again, note the results and go on. So the next step is synthesis.
Again?
Yeah.
It's Paco here. Can you say a bit more about those bias corrections?
So what we try to do is, for instance, for temperature, we allow for an offset in the mean, and then we check whether the PDF is the same after correcting for the mean. And for precipitation, we allow for a multiplicative bias correction and check whether the PDF can be scaled to bring it into agreement with the observations. So if the width, the dispersion parameter, the sigma over mu, is very different between the model and the observations, we cannot do that. But if both the variability and the mean are 10% too large, we don't care, and we just scale by 10%.
And there is no spatial correction of these signals, is there?
Not yet, no. We either do a point or an area average, and we concentrate on the time series. So maybe I should have emphasized this in the way we see event and attribution is to look at a class of events, not the exact same event that occurred. So, for instance, for the Paris floods, we just take the average rainfall over the Seine basin in 3 days, and then look at the class of events in which the rainfall in this season was the same or higher than the observed one. So you look at all the events that gave lots of rain there, and not only the one in the summer of 2016 that actually gave the rain. I do not know how to do it for a specific event, and I also think the results are more useful for our users for the class of events, because the people in Paris don't really care what kind of weather situation gave all the water that's coming down the Seine if they're almost being flooded. I mean, in fact, in this case, Paris had hardly any damage at all because of the good protection and the good water management. So the final step is then the synthesis. For the French floods, we made these tables where we had the risk ratios, the increase in return times, or the improbabilities, decrease in return times for the different models. And you can see we used 4 different models or model ensembles. And we used one of them actually in 2 different ways, both on the trend and as the difference between the actual climate and the counterfactual climate without anthropogenic emissions. And later we found that there is a better way to present it, and this is from a paper that will soon appear on the Boulder floods. And if you make these beautiful horizontal bars, you can see at a glance whether there is agreement between the different models and the observations. And then you do your, you check whether there's a good enough agreement. If the main variability is natural variability, you can combine all the input and make a multi-model weighted average. On the left-hand side of the risk ratio, so the increase in probability. On the right-hand side, the intensity. And this is one of those events where, in fact, the increase in probability or the increase in intensity is much less than you would expect from Clausius-Clapeyron. So there's a big change in the models, and also maybe in the observations, although the observations are, the uncertainty is fairly large, that counteracts the increase in moisture in the atmosphere. And in contrast to what some people think, you cannot just use Clausius-Clapeyron, and actually you get a much smaller increase than that here in the middle of the continent than you would expect just from very simple reasoning. And again, so if you do this as a surface, you have to convert to a common measure, for instance, pre-industrial to now. Judge agreement between the models. Is it all natural variability? Natural variability always plays a big role in these kind of studies. Or is there also a model spread? Compare the trends of the models with the observed trends and compute a multi-method interval. Of course, there's a real possibility. We had that with the German floods, that there's such a disagreement between the observations and the models, or between the models, that we cannot make a statement. You just have to be honest and give up. And then you make this attribution statement, and this will be supported on the Climate Explorer in the near future to do all these just simple statistical computations, but pretty error prone, especially if you have to do it in a hurry. So I think we should automatize this. The user groups for which we do this is in first thought, we was only the media, and their main request it should be timely, days to weeks, depending on the size of the event. We were very pleasantly surprised with our Louisiana study, which came out as a NOAA press release 3 weeks after the event. It took us 2 weeks to do the analysis because it's a very complicated event. And then they delayed it for a week because of a hurricane, and it was still considered very relevant 3 weeks afterwards. So that means we don't have as much time pressure as we feared we would have. It turns out that decision makers are also really interested, especially in countries with a less established infrastructure. And they, of course, get a lot of information from the media, so that's often the same outlet. But again, it needs to be timely. Our Red Cross and Climate Center partners tell us that decisions how to rebuild are often taken within months after an event. And in order to influence these decisions, it has to be within a few months, preferably a month or so. And of course, it has to be trustworthy. I mean, the source has to be considered trustworthy. Originally, I didn't think this would be a useful outlet because decisions should be based on projections, not on attributions. But the people working in the field tell us that the projections are made much more acceptable to people if you have an attribution statement about the event that just happened. So purely logically, it's unnecessary, but in real world, it helps a lot. Insurance companies are interested, but only if it's trustworthy. And strangely, their definition of trustworthy is it comes from the National Meteorological Agencies. They don't trust researchers. They do trust the KNMI and the Met Office. I don't know why, but this is their rule of thumb. And of course, litigation lawyers are really interested that it has to be extremely trustworthy, and they don't care about the time scale. It can be 10 years later. The obstacles we see for making this operational, because we're working on making this operational, we submitted a proposal for ERA4CS, and inside KNMI, we're working on procedures to let the weather room do this. First, you need a lot of meteorological, climatological, some statistical knowledge. Basically the same as in seasonal forecasting, so that shouldn't be a big obstacle, but there are people who have that knowledge, no problem. You have to have ties to the impacts community to really define your event well, and hopefully later also model the impacts. But the big problem is the model biases. The model biases are often large. For instance, heat waves in Europe, the model trend is less than half the observed trend. What do you do? And you cannot easily apply model corrections. And how to handle those, I'm not sure we can put that into a procedure and hand it to operations and say, just follow this procedure. So our plans is to really move attribution of simple extremes to operations as quickly as possible, support that with the development of tools, observation, model data availability, fitting tools, synthesis tools. and go on ourselves doing research for more complicated extremes, which a lot of demands, hurricanes, snow, even hail, tornadoes, if we can do it. And at the moment we can't, but maybe in a few years' time. And the problem is the definition of the simple extremes. I mean, people think that heat waves are simple, but we looked at it and they're not. In Europe, as I said, the trend in heat waves is twice the observed trend is more than twice the model trend. How do you do an attribution? So that's the fun part about event attribution from a science point of view. It forces you to address these questions in a really concrete way. In the United States, of course, it's the opposite. The eastern two-thirds of the United States, there has been no trend in heat waves the last 100 years or so. And the models also show a positive trend. So there the models overestimated. Why? Is it forcing? Is it decadal variability? I don't think anybody knows. It forces us to address these issues. This, cold waves, are they simple? Well, they have a very bad signal-to-noise ratio, and circulation trends are pretty uncertain. There are people claiming all kinds of things about sea ice, and other people claiming that's nonsense. Winter rain extremes, actually, these are among the easiest. Circulation trends are uncertain, but they seem to be doable. Summer rain extremes, the small-scale ones, really thunderstorms, you need convection-permitting models. We don't have those yet. So there are a lot of when we actually try to transfer it to an operational setting, we run into all these problems that, of course, it makes it more difficult. Of course, we think we know everything best, and we have to let go of that as well. Yeah, it's still the goal for the next few years to really make this into a climate service and answer the questions that really come out from society every time an extreme event happens. Okay, thank you.
Thanks, Geert Jan. Questions for Geert Jan? Okay, well, I have one, but it has more to do with the part that you didn't talk about, so the part that Climate Central is doing. So somehow Climate Central is working on the communication and of these results. Mm-hmm. So what is your experience, and this is building a bit on what Andrea has been talking about before, what is your experience about the challenges to communicate all this to the outside world?
It's tough. We chickened out a bit by outsourcing the communication to a third party, i.e. the journalist. So our aim is to communicate on such a level that a good journalist, preferably a science journalist, can understand it and ask him or her to translate it to something that the general public understands. And for instance, there was a lovely article in the New York Times, and one of our partners from Oxford showed it to her mother, and the mother said that it was the first time ever she understood what her daughter was doing. Yeah, we put an intermediate between us and the general public. Climate Central is doing a lot of testing. During the communication on the Louisiana floods, they did a big experiment on the mechanical Turk and check whether people actually understood what we said. And the results should be coming in shortly. So we found that the FAR is totally unintelligible, so we don't use it anymore. But even the increase in probability, it turns out that most people think it's just a factor 2 more, whatever you say. And so there are big communication barriers, yes.
And the other aspect, again, related to communication is how to, but I was asking before Andrea about the communication of uncertainty in climate predictions and climate projections. Do you see any difference in the need for communicating uncertainty in attribution statements?
No, it's exactly the same, except that we have been under a lot of pressure to be conservative. So there has been this tendency to only report lower boundaries, like the probability is increased by at least a factor 2 or a factor 4. And personally, I am trying to get away from that because the at least so often gets lost in translation, and you read back your articles, and even on the own KNMI website, the at least is gone, and it says the probability is increased by a factor 2. I think we should be not under pressure to be conservative, but be honest to communicate the best estimate plus uncertainty and not only the lower bound.
It sounds very similar to the pressure to hedge when you're doing forecasts. so that you stay closer to climatology and reduce the risk of being wrong.
There are some nice articles about this, the seepage articles and the pressure on IPCC. What was the article that to be the least surprise? I think it was called the path of least surprise, and I think that's a political pressure that, in my role as a scientist, I should try to ignore as much as possible, however difficult that is.
Yeah. Again, are there any questions for Geert Jan? No? We have just a few minutes left, and I wonder if both Andrea and Geert Jan would be happy to at least address the first question that we had in the program. So the one that reads, which challenges for climate modeling and observations are raised by climate services? So Geert Jan, we can start with you, and you said that you submitted a proposal for the ADA 4CS call, somehow trying to put together this attribution or real-time attribution system within a climate services context. So what are the challenges that climate services are raising in your case?
Well, my part of the proposal is to actually build a technical infrastructure. So it's really a development. We're pretty good at doing research, and we're not so good at transferring that research into development and finally into services. And this project really tries to address that. So, and then the second frontier is the one that Andrea can comment much more on. It's the communication side. From the event attribution point of view, that's also politically very challenging, because the Met Office really want to keep that in their own hands. So this proposal explicitly excludes the communication to the public, because the Met Office, the UK Met Office and other Met Offices do not want to put that into the hands of a climate service. They want to do it themselves.
If that's the case, what will happen with the private sector?
Sorry, but
what I mean is that if the Met Services want to keep the attribution statements under control, how are they going to control the private sector?
The private sector.
Yeah.
The thing about event attribution is that there's no money in it, as far as I can see. Everybody wants to know the answer, but nobody wants to pay for it. So it has to be either a public service or not exist. So
basically, one of the challenges that climate services is raising, or at least the climate modeling and observations part linked to attribution statements, is that there is not going to be any feedback or any funding feedback into it.
No.
Okay, that's an important factor. Andrea, do you want to comment on this question?
So drawing on obviously experience from the EUPORIAS project, I would say that one of the challenges is definitely that user demands and what can be provided or reasonably, reliably and honestly provided by the sciences isn't always going to mesh. So users may want something that it's not really possible to provide it at this spatial and temporal resolution. In terms of addressing that, obviously I come from the more social sciences perspective, so I don't know much about the side that would involve making sure that the science can provide those things or can provide those things better. But I think it comes down to a lot on expectation management, finding out whether if a particular data on a particular variable or impact that a user would like can't be reasonably provided, is there something else that could be provided that would do the job?
Okay, so if I may ask, how is your communication work affected by the fact that there is climate information, but let's say projections coming in different ways. So how have you were talking about expectation management. So when you have to convey a message about climate projections a few years ago, and then in a few years' time, you are going to again provide another message about climate projections, but which is slightly different. How do you, from what point of view, this is a challenge to you?
So I'm not aware of any research that can provide a definitive recommendation here, but I think that the important thing is to obviously not hide the fact that things are different, but to perhaps comment on what's been consistent as well, perhaps give, as can be reasonably done given the complexity of the science, some explanation as to why things might be different.
Okay, thank you. Any comments from the floor? Okay, so if that's the case, I suggest that we stop it here. We've been already going on for more than 1 hour. So I think the only thing left is to thank everyone for participating, for your patience with any technical issues that might have occurred. And we'll invite you to join us again for the next webinar in, I think it will be in around 3 weeks in November. So we're still trying to close the roster for that one. So there are a few candidates already, but again, it will be something fairly basic, but that also triggers discussion and brings together people with very different experiences. So thanks very much, in particular to the two speakers, and well, have a nice weekend.
Okay, goodbye.
Bye. Thank you.